ladies and gentlemen, class recording has started. So, today, we get started in on Unit 4, Chapter 4 of your book, that deals with motion in 2 dimensions. The first 2 chapters that we've done, well, the first chapter was like math and stuff like that, but the second chapter and third chapter dealt with introducing the ideas and the measurements for motion. How do we describe motion? How do we measure motion? What do we have to do to accurately describe a moving object, etc., etc., etc.? And we introduced things like displacement and velocity and acceleration and all those kind of things. Those concepts do not change when we move from 1 dimension into 2 dimensions. Acceleration is still acceleration. Velocity is still velocity. Displacement is still displacement. But how we express them in 2 dimensions and how we define them in 2 dimensions does need to be changed a little bit. Remember that everything that we've done up until this point has only been in 1 dimension. We've been on a straight line. And when you're on a straight line, you've only got 2 options. You either go this way or you go that way. And so that makes things a little bit obviously simpler than when we have multiple options as far as which way we can go. And we're going to start in on that today. How do we start accounting for all of these new multiple options? Okay? Good there? All right. We are going to start here. I believe I've been telling you over time here that this book comes with a lot of good resources, and I really like a lot of the resources, and one of those is PowerPoint slides. Generally, the PowerPoint slides that come along with books I have not liked a whole lot. I just don't think they do a really good job, but these ones do a pretty good job, and the pictures that they use are actually straight from the book and stuff like that, so it makes it a little easier to come all back to what we're doing. All right. So, that being said, let's go here. We talked about that physics is the study of the physical world, and part of studying the physical world means that we make measurements of said physical world. And that's true of motion within that world. And sometimes we measure that motion and we get a value and it describes something about it, like how far it went or how fast it was going or something like that. And we refer to those values as scalar quantities. Not a new term, one that we've already discussed, but when we talk about something being a scalar, we can measure it, and we give it assign it a value, and we put a unit on it, and that's great. Oh, one thing about the PowerPoint slides from the book, they are kind of wordy, so if you can, if you paraphrase, that would work too, right? As obviously, what you write down is completely up to you. If you want to write down anything, you don't have to. So we start off measuring values about the physical world, and we call those values scalar quantities. And things like volume and temperature and time, these are all scalars. But as we saw in our discussion about mechanics and measuring motion and stuff like that, sometimes it's not good enough just to tell us how much of something, right? Things like velocity, right? There's a difference between traveling 10 meters per second one way and then traveling 10 meters per second in the other way. We have to distinguish that somehow. And acceleration, there's a difference between a positive 2 meters per second acceleration and a negative 2 meters per second acceleration. So sometimes scalar quantities aren't enough to accurately describe what's going on in a physical situation. Sometimes we need more. And that more is the whole direction idea. And that takes our scalar quantity and turns it into a vector quantity, right? So we take the magnitude, the number that we've measured, and then more accurately describe along with that number the direction that it was going. Now, like I said, we've taken our scalar value and turned it into a vector.
So a vector quantity is just something that tells direction?
Well, along along with direction, it also tells magnitude, right? So it not only tells how much of something, but also tells which way of something, right? So really, it's like the difference between speed and velocity, right? 10 meters per second is a speed, but 10 meters per second north is a velocity, right?
Yeah.
Yeah, like that doesn't change. Like the idea of vector scalar doesn't change, but now when we go to 2 dimensions, how we describe it is a little different. Because we talked about that when we were in 1 dimension, when we're on a straight line, how many choices do we have? 2. We got 2 choices, this way or that way. And how did we distinguish those 2 choices from one another?
Right, with you positive.
Positive, negative, right? But when we move into 2 dimensions, now there's a lot more choices, right? It's not just 2 choices. Now we've got all kinds of choices, up, down, side, side. So there's got to be some other way to distinguish that. In 2 dimensions, for instance, right? If I ask you a question like, hey, where's the library at? And you answer, oh, it's 1 kilometer from here. Is that enough to get me to the library?
No.
Yes.
Maybe.
Maybe, right? Because along the lines of that answer, right, the library could technically be anywhere on this circle that has a radius of 1 kilometer, because any place on that circle is 1 kilometer from here. But if you add that the library is 1 kilometer northwest of here, that eliminates these possibilities down here and now more accurately describes the location of the library. Right? So, representing that value brings us to vectors in 2 dimensions, right? So, Julie, like we just discussed, right? A quantity that has both length and direction is called a vector. Magnitude and direction, right? How much and which way. Before, we distinguished the directions just by positive and negative. But now, we're going to use arrows to represent those vectors. Those arrows will help us both represent the magnitude and the direction. We try to draw the arrows proportional to the magnitude. So if we have a velocity of 4 meters per second northwest and a velocity of 2 meters per second southwest, we should try to draw our 4 meters per second arrow twice as long as our 2 meters per second arrow. Does it have to be exactly twice as long? No. But it helps us just keep track of the relative proportions of those vectors. And then, which way the arrow points tells us the direction of that vector, or the direction of the vector's effect. So now, instead of just positive and negative, now we're going to expand that out and say, okay, it's not just positive or negative, it's this long or this far in this direction. And we'll use the arrow to represent that. But keeping that in mind, that does not change the definitions of the terms and concepts that we used to represent motion in the previous chapter. Okay? All of those terms and all of those concepts that we introduced in the previous 2 chapters about measuring motion still have the same definitions. Just how we apply them in 2 dimensions might change a little bit. For example, so here's a picture of your location and the library's location. And we've drawn an arrow from here to there, from you to the library. What would that arrow represent? Displacement. That arrow represents displacement. Because we said that when we define displacement, what do we have to know? What does the displacement depend on?
Distance.
Where you start and where you end, right? Your starting position and your final position. This is where you started, this is where you ended. So this arrow that they have represented by R, why R I'm not really sure, but R represents the displacement. But we could walk 1 kilometer northwest and get from where we are to the library. But in real life, would we be able to probably walk 1 kilometer northwest from where we started to get to the library? Maybe, right? But if we're like in a city, there's things like trees and houses and streets and cars in the way, right? So generally, you're not going to just walk from where you start to where you want to be. You're going to have to, follow the streets and go along, whatever this is, Birch Street, and then go up 2nd Avenue, right? We would probably walk along this street and then along this street. While this arrow represents the displacement, what would these 2 arrows represent? Distance traveled, right? This is the length of our actual path. This is the difference between where we started and where we finished. We talked about in one dimension, displacement and distance traveled end up being the same as long as what? What was a situation where distance and displacement are the same? Logan. Straight line, right? They become different when we do what? We don't go in a straight line, right? Or if we turn around and go back the other direction, right? So here, right, not a straight line. And now displacement and distance traveled are different, okay? These 2 arrows here representing the distance traveled are related to this displacement vector. Because whether you go straight from here to here, right, from your starting point to your ending point, or whether you go along this path, where do you eventually end up? Library, same spot. So these things are related to one another. Okay? We call these separate trips the components of this vector. So we would say that these separate trips are the east-west and north-south components of this displacement vector. If we go 1 kilometer northwest to get from where we started to where we finished, that's actually 2 separate trips, right? If you go northwest, you actually have to take 2 separate trips. What do you have to do?
Turn.
Yes, because you have to start off going how? If you want to go northwest, you got to do what?
Go north first or west.
You have to go north, and then you have to go west. Or you have to go west, then you have to go north, right? That vector that represents the displacement is actually a combination of 2 other vectors. And the combination gets you to where you want to be. We refer to those combination vectors as the components. So, when we resolve a vector, that means that we find its components. The components are the lengths of the vectors along those specified directions. If we talk about our trip to the library in the northwest direction, that trip has a north component and a west component, because the 2 together make the final destination. Regardless of whether you talk about just the straight vector from start to finish, or whether you talk about the individual components, you will end up in the same spot. Either one of them is appropriate for describing the vector. It's just a matter of how we describe it. So when we resolve a vector, we find its components. And that means finding the individual trips that will combine to get us to our ultimate final location.
That's like a hypotenuse, like pretty much.
So here, right? Sorry, I'm still writing. So this vector down on the left, 1.5 meters in this direction, 1.5 meters at this angle of 25 degrees is the equivalent of going 1.36 meters this way and then 0.634 meters in that direction. Okay? How are we going to find these? Well, you have a horizontal part, you have a vertical part, and then you have the vector, right? We can make one big right triangle. Okay? Sorry, did you guys not finish writing that down? Sorry. Go ahead, finish writing it down.
SOHCAHTOA.
SOHCAHTOA, right. Good old SOHCAHTOA.
Were you good at math then? Better at math or science? Science probably.
I enjoyed science more than math, but because now that I realize all the stuff you do in math, it's just kind of like you do it, but then you go to science, you're like, oh, that's why you do it. So, all right. So you don't have to write all this down, but this blue line represents our vector. This angle, labeled theta, represents the direction, right? Theta is just an unknown value, right? We can use it just like x or y or z or whatever, right? But once you resolve this vector into its components, you end up with a right triangle because these components are perpendicular to one another. So if we wanted to find the two sides of the right triangle, we can use our trig functions to find those two sides. For example, if we want to find this horizontal component, right, which is labeled Rx, R sub x in this picture, in relation to the angle that we know, what side of the triangle is that? It's the adjacent side. So if this is the adjacent side, that means we would use cosine, because cosine deals with the adjacent side of that triangle. Okay? And then, if we wanted to find the vertical component, right, the y component, what side of the triangle is that in relation to the angle? It's the opposite side of the triangle, right? So in that case, then, we would use the sine value, because sine deals with the opposite side of that triangle. Okay? Good there? So taking that and relating it back to our library trip. So here's our trip to the library. That oh so helpful person at the beginning of the question told us that it was 1 kilometer from our location to the library. But then after a little bit more prodding, right, we find out that it's 1 kilometer northwest. So if we say it's northwest, we probably want to say that it's about it's halfway between west and north, right? So that being the case, what would this angle be right here?
45.
That would be 45. Okay. But as we've discussed, that's the displacement, right? 1 kilometer at 45 degrees northwest. Okay? But that doesn't help us as far as getting there, right? We really have to go this way first, and then this way second.
But shouldn't that be the
Right.
same?
Well, in this case, yes. Julie, go ahead.
Will hypotenuse always tell displacement?
In this case, yes. That's a good question. Will hypotenuse always tell you displacement? Yes, because Julie, the displacement only depends on where you start and where you finish, right? So that's always going to be a straight line from where you start to where you finish. Okay? Now we'll learn that later this week. It might not always make a nice triangle for us, and we'll learn how to deal with that. But for now, it's just going to be a triangle for us. Okay? So first, let's take x, right? In relation to the in relation to the angle that we know, what side of the triangle is x? It's the adjacent side, right? Meaning, we can use our cosine function to find out that side of the triangle, right? So I'm going to go ahead and plug in things I know. I know that the angle is 45 degrees, right? I know that the adjacent side of the triangle is unknown. We call that x. and then I know the hypotenuse is 1 kilometer. Okay? So then, rearranging and getting x by itself, we just multiply each side by 1 kilometer, multiply each side by 1 kilometer. Cosine of 45, you just plug that into your calculator and you find out what it is. Okay? And make sure your calculator is in degrees. And then you multiply it by 1 kilometer. Okay? And you should end up that the x component is 0.707 kilometers. Okay? Good there?
So then you can just right away put
So 2 ways we can do this. Okay? Let's do the long way first. All right? As far as y is concerned, in relation to this angle, right, y is the opposite side. So we can use our sine function, because sine relates the opposite side of the triangle with the hypotenuse. This is the angle we know, so we plug that in, right? We don't know the opposite side, so we just leave that as y. And then the hypotenuse is still 1 kilometer. Multiply both sides by 1 kilometer, right? And you plug sine of 45 into your calculator, and what you find out is that they're the same. Okay? So that's the long way of doing it. Now, if you remember your geometry stuff, right, you can take a shortcut. Because in this triangle specifically, what kind of triangle is this? It's a right triangle, but it's a 45, 45, 90 right triangle. And what do you know about the sides on a 45, 45, 90 right triangle? They're equal to one another. And so we find out that is the case. Okay? So we said that our displacement is 1 kilometer at 45 degrees northwest, but what would be our distance traveled for this trip?
1.4. Oh, 1.414.
Okay?
Big bud.
Because what do we do to find the distance traveled? Just add these two components. Okay? Notice the concept doesn't change, but how we describe it or how we define it in 2 dimensions does. Good there? Okay. One last thing. All right. So, all right. Here's a picture of you getting from home to school. Okay? I'm going to take this picture and put it here. All right. So, in this case, you walk 200 meters east, then turn and walk 300 meters north, and that gets you from home to school. What's your distance traveled for your trip from home to school?
500.
Your distance traveled is 500 meters, right? Does that make sense? But is that your displacement? No. This value represented by this vector, which I'm going to call in and make it purple.
Probably the square root of 1,300.
Tell me it's wrong. Just tell me it's wrong. Even though it's right.
Oh yeah, it is.
It is? It is?
Yes, but let's go through and do
No,
it.
tell me it's wrong.
That's right.
It's right, actually. So.
Tell me it's wrong.
All right, so
You're wrong.
how are we going to find this vector? What's the first thing we're going to do? Okay? We have to find the length of this vector, right? So, to find the length of that vector, we can use Pythagorean theorem, right? A squared plus b squared equals c squared. Okay? The only requirement, right? Remember, which side does c have to be? C has to be the hypotenuse, right? So, all right, we can go 200 squared plus 300 squared equals, in this case, they've labeled that hypotenuse as r, so it's r squared. Okay? You go through, you do your math, and you get that r is equal to 361 meters. Okay? But we're not done, because our vector for displacement also has to include what?
Direction.
Direction, right? So this angle right here that I just called theta has to tell us which direction we're going to go. Okay? Now, in relation to this angle that we're looking for, what side of the triangle is this? That's our adjacent side, right? And then that means that this side of our triangle is the opposite side. Now, since we've already gone through and figured out the hypotenuse, you actually have a couple more ways that you can do this. But if we stick with the information that was given to us, what trig function relates opposite and adjacent together? Tangent, right? So tangent theta is equal to opposite over adjacent, right? So katoa. So we start plugging in things that we know. Tangent is just tangent, but now we don't know what the angle is, right? That's our unknown in this problem. That then equals the opposite side of this triangle, which is 300, over the adjacent side of this triangle, which is 200, right? And then you end up with tangent theta is equal to 1.5, right? But we don't want to know tangent theta, we want to know theta, right? So that's when we are going to take our arctangent, okay, or the inverse tangent. If we take the inverse tangent of this, these two cancel, and we're left with just theta. But if you take the arctangent of one side, you got to take the arctangent of the other side, right?
True.
So you plug that into your calculator, keeping in mind that you got to be in degrees, right? And when you do that, you should end up with 56.3. That means that this angle here is 56.3 degrees. Okay? Good there? So our distance traveled is 500 meters, but our displacement now is 361 meters, 56 degrees north from east. The north from east is there to distinguish which 56-degree angle are we talking about. If you start off with from east, right, north from east, that means that originally I was going to be facing east. And then I'm going to turn. Which way am I going to turn? Towards the north. So this is turning towards the north from east, 56.3 degrees north from east. Okay? Yes, because you got to distinguish what angle we're talking about here. Okay? We'll definitely do some practice with this, Tam. So it's not just. Yeah, don't worry. Well, yeah. And there's some other ways that we distinguish angles, and we'll kind of look at those a little bit as we go along. So, for tonight, first, a couple pages to read from the book, page 113 to 118, and then 5 questions. Those are all conceptual questions about vectors and component vectors and stuff like that. We will do practice in class tomorrow.